Hello, my name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki has registered more than 300,000 members. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled Unpacking System Performance. Supercharge your systems with lossless compression IPs. Our speaker today is Dr. Calliope-Louisa Sotiropoulou, Sales Engineer and Product Manager at CAST. Calliope specializes in image, video, and data compression and IP stacks. Before joining CAST, she worked as a research and development manager for the aerospace and defense sector. She has a long academic record as a researcher, working for various projects including trigger and data acquisition system of the Atlas experiment at CERN. This is a live webinar, so put your questions or comments in the chat box, and we will respond during the Q&A. You will get a link to the replay after the webinar. Okay, let's get started. Over to you, Calliope.
Thank you, Daniel, for this introduction, and good morning or good afternoon, everyone, depending on your time zone. Thank you for participating in this webinar about how to supercharge your systems with lossless data compression IPs. I will start with a big thanks to SemiWiki for offering CAST this opportunity for this webinar, and especially Daniel for helping us organizing the webinar for you today. And I will start with an outline of the presentation for today. The first thing that we will discuss is what is lossless data compression, the definition of lossless data compression, and why we use it. Then we will discuss the differences between software and hardware implementations, and what are the disadvantages of the advantages between them, and why we should choose hardware for our embedded systems. Then we will proceed on how to choose the right algorithm for a design application, and what are the characteristics and the parameters we need to decide. We will then see some real-life examples about how to integrate the core in a system, and some real-life implementation results for actual CAST customers, and also further examples of implementations. Well, we will finally conclude with a brief description of how CAST approaches the lossless data compression IPs, and what solutions we can offer to developers and designers from the CAST portfolio. So let's start. So what is lossless data compression? Lossless data compression is an algorithm that when it is used to compress and decompress a file, the output is exactly the same as the input. The reconstructed file is exactly the same 100% as your input file. This is used when you have zero tolerance for errors. Your application is as such that you cannot have even one single bit of difference between input and output. The lossless data compression algorithms are usually a two-step operation. The first step is some kind of search algorithm. You define a history window in your data file where you identify patterns that are repeated, and thus you eliminate redundancies. The history window is the size of the part of the file that you will do your search, and it has an impact on both the size of the core and the compression ratio, as we will discuss later. And then the second part of the algorithm is the encoding when the actual data reduction takes place. The encoding can be different kinds of algorithms, such as Huffman encoding, finite state entropy encoding, or dictionary encoding. So why do we use lossless data compression? Lossless data compression algorithms have always been used, but in the past there were kind of niche applications, especially like for big data centers and such. But lately we see a trend and a bigger need for such algorithms because we have a trend. We see the trend of AI applications, specifically machine learning, where we have the need to process huge volumes of data. And specifically for machine learning, we have the need for precision and accuracy, where absolutely what you need for data compression is lossless data compression, because you cannot afford to have any errors in your training. Another application we use where your lossless data compression is used is storage optimization for data centers and edge devices. As you obviously understand, in data centers, huge amounts of data, huge volumes of data are stored. And therefore, in order to store this data, you need hardware to store your data. By using lossless data compression, even if you manage to reduce the volume of data to 50%, you save huge volume of storage space and, of course, money, because you need less hardware. We also use lossless data compression in networking. This is especially true in networks where the bandwidth is limited, such as in automotive and aerospace applications. There you have sensors that bring you sensitive data that are critical for the operation of the car, of the airplane, such as LiDAR or radar data or other kinds of sensors. And all this data need to travel through a network with limited bandwidth. And obviously, you need to compress in order to have better bandwidth efficiency, and this needs to be lossless. This also happens when you have the need for real-time responses in real-time applications. This is the case for any kind of control system, also the case in AI, and especially in finance trading applications, where even if you can save some microseconds in your response time, it can make difference of millions. We also use lossless data compression for energy efficiency. We use it to reduce power consumption. And implementation of a lossless data compression algorithm on hardware is much more efficient than on a software on a CPU. And it saves you so much power, which makes it much more efficient and economic, especially in data centers. This also means that you have better thermal management. You have less need for cooling, which also saves you money. Imagine huge data centers where the need for cooling is very big. So with better power consumption and lower thermal cost, then you have a much lower cost in management. The same applies to smaller applications, such as wearables, where also thermal management is critical, because obviously you cannot have a wearable that can burn the user. So let's discuss the software approach. Which algorithm is the right one for you? We discuss here 4 different algorithms, such as GZIP, LZ4, Zstd, and Snappy. They are all part of the same family because they have the same search algorithm as a first step. Remember, we discussed this in the first slide. This search algorithm is called LZ77. So they have different kinds of algorithms, such as the LZ4 and Snappy. These 2 algorithms have a low compression ratios, we can see here. They have a low software latency and a high software speed. We have another algorithm that's called Zstd. This in software gives you a high compression ratio, but at the cost of high software latency and moderate software speed. And then we have the 2 different flavors of GZIP with the dynamic Huffman tables and the static Huffman tables. The difference between the 2 is that the first one, the dynamic one, will give you a higher compression ratio at the cost of software latency, while the static one will give you a moderate software compression ratio with a moderate software latency. They both have moderate speed in software. So let's discuss why we should prefer hardware over software. Well, obviously, software is flexible. You can implement different software algorithms in your CPU, and whether you change your mind, you can choose another software. But especially when we discuss the high throughput applications that are necessary today for applications such as data centers and AI, this will create a very high load in your CPU, and your CPU will need to dedicate all of its resources on this specific algorithm. This will also mean that the throughput will scale poorly, especially for this kind of throughputs that we need today, like multi-gigabits per second. You can only scale throughput on a software when you have a higher performance CPU, or when you add more CPUs on your design. And another big disadvantage is that you have unpredictable latency, because on your software, on the CPU, you will need to access external memories, you will need to access cache, and you will have other things also running in parallel that need to access the memory bus, etc. And that will give you an unpredictable latency in your application, which in several cases that we discussed before is critical. This doesn't happen in hardware. Hardware will offer you always deterministic performance. It will be deterministic in latency, deterministic in throughput, and deterministic in power. Once the hardware is defined for your specific specifications, for your specific requirements, it will always give you the same results. Hardware cores for lossless data compression can scale to multi-gigabits throughput. Of course, this will come at the cost of resources, but it can be done with lower power consumption, much lower power consumption than in software. And the cost of the hardware resources would be much, much lower than instantiating and needing multiple CPUs. You will also have lower power consumption compared to software running for the same performance in a CPU, and the hardware for lossless data compression will always be real-time ready. So now let's study the table we saw before, wearing our hardware glasses on. So what's the difference here? Before we were discussing the software latency and the speed. Now we discuss hardware latency and resources. And we have the same algorithms to discuss. So again, LZIP4 and Snappy have the low compression ratio, will always give you lower latencies, and will always give you lower resources requirements. Zstd will give you higher compression ratio, but it will have a high latency, and it will require more resources, many more resources, because the Zstd has more than one encoding algorithm as a second step, which by default require more resources than the rest of them. GZIP, with its two flavors, will give you high compression ratio for dynamic Huffman tables with higher latency and high resources requirement, while static flavor will give you a moderate compression ratio with a lower latency that is comparable with LZIP4 and Snappy algorithm latency, and lower resources, which again are comparable with LZIP4 and Snappy algorithms. So we have a lot of information now. We know how these algorithms play with latency and resources, but is this enough to choose? The truth is that no, it isn't enough to choose, because the algorithm we will need for application and the configuration we will require will also depend on the data set, on the data type, and on the file size. And of course, it will also depend on the algorithm configuration. So how do we make an educated choice? This is what we did to assist the developers that rely on cast cores. We use the Silesia compression corpus as a reference. The Silesia compression corpus is a test bench with various different files that is open source and available in this link here. You can access it and have a look. And we used all these algorithms we discussed before to calculate the aggregate compression ratio. Mark this difference, please, because we don't use the average compression ratio, which is basically the compression ratio of all files divided by the number of files, but the aggregate one, which also takes into consideration the file size. This is much more helpful when we discuss throughput and performance of embedded systems, because the file size will impact severely the throughput of your file system, of your final system. The Silesia corpus is a very objective way to evaluate different lossless data compression algorithms, because as you can see here from this list, it includes various different kinds of files and data types coming for different application spaces. And all these files present different compression ratios using different algorithms, so it is a very objective way to judge. So here's what we did to start with. We used software of these 4 or 5 compression algorithms we discussed before, ASIC, Snappy, GZIP with its 2 different flavors, and Zstd, to calculate the aggregate compression ratio of Silesia corpus files. We configured the software to use the same history window of 32 kilobytes for all these different algorithms in order to have an objective comparison, because all these algorithms have a different maximum size of the history window, which is the part of the file that you can search for redundancies, as we said before. And having the same history window makes the comparison more objective. And as we will discuss in the following slides, the history window will have a high cost in the hardware implementation. So here is what we found out. The GZIP algorithm with dynamic Huffman tables has the higher aggregate compression ratio for Silesia corpus. Zstd and GZIP with static Huffman tables have similar compression ratios and come second. As you can see here, GZIP comes with 2.76 and Zstd with 2.79. And ASIC and Snappy have the lowest compression ratio, as it was expected by their algorithm, which is pretty similar. As you can see, the difference is very small. It's 2.08 to 2.07. So what happens in hardware? A lossless data compression IP implementation has a processing element that will require to implement a history window to do the search, and an encoder in order to achieve high throughput for the performance, as we discussed, for the multi-gigabit per second implementation. You will need to instantiate multiple cores. This might be multiple cores running in parallel as embedded cores, or one big core with multiple internal processing instantiations. So the cost in memory resources of using a big history window will be higher, the higher the number of instantiations you will need of these processing elements. Think about it. In the high throughput implementations, you might need 20, 30, even more processing elements to do the compression for you. And each compression element can have 32 kilobytes of memory or more. So you multiply 32 kilobytes by 20, 30, or 40, depending on the IP throughput, in order to find the memory requirement of your application. If you add to this requirement for dynamic Huffman calculation as well, you will even need more memory, because dynamic Huffman calculation of tables will require more memory resources. So how do you save memory? A good strategy would be to limit the search to a smaller window. So reduce your history window size. So here's what we did to understand the impact of limiting the history window size on our IP cores. We have here a study of all these algorithms, GZIP with the 2 different flavors, by reducing the history window from 32 kilobytes to 1 kilobyte. You can see here that the impact of reducing the history window is smaller on the lower compression ratio algorithms such as ASIC and Snappy, and it is higher on the higher compression ratio algorithms such as GZIP with dynamic Huffman tables, Zstd GZIP with static Huffman tables. The impact, however, between each algorithm is different. So what a developer must do in the end is study this and make a compromise on the availability of the memory resources and what's the compression ratio that the application must target. So there has to be a compromise between what the number of memory resources you are willing to sacrifice on your system, and the compression ratio you must target. This is not the only thing that impacts compression ratio. There are several applications where the files are limited to a specific size, such as applications for data centers or applications for compression for solid-state drives, where file paging is very commonly used. The sizes of the files in such applications are small. It can be 4 kilobytes, 8 kilobytes, or 16 kilobytes. So what happens in such cases? For these small files, the history window doesn't need to be larger than the maximum file size. This is obvious if you think about it algorithmically, because you don't need to search an area in your file that is larger than 4 kilobytes for redundancies. The maximum file size is there. So what we can see here on the graph on the right side of the slide is the impact of the reducing the history window size from 4 to 2 to 1. As we can see, the impact is much lower than in the previous case where the files were larger. And again, the impact for the lower compression ratio algorithms is lower, while it's larger for algorithms such as Snappy, such as Zstd and GZIP with dynamic Huffman tables. But in reality, again, it's a compromise, and we can see by this graph that we can easily define a rule of thumb, let's say, that in such case, we can use a history window of half the file size without compromising the compression ratio much. So let's now proceed with what CAST can offer as a lossless data compression portfolio. We have an extended portfolio which comes from our long experience in this application field. Our ZIP cores have been in the market for more than a decade. These cores have been productized tens of times on both ASICs and FPGAs. We have customers that have productized these cores of speeds of over 400 gigabits per second. They have productized on the newest process nodes of 4 nanometers and 5 nanometers, and we have currently customers that we cannot name, obviously, that are taping out in 3 nanometer technology and designing 2 nanometer technology. These cores support GZIP, zlib, and deflate protocols, and can be configured to reach over 100 gigabits per second on FPGAs and over 400 gigabits per second on ASICs. The limit on the FPGAs is much higher now because we have new devices that come into the market for the major vendors. The new devices by both AMD and Aldera that are really big and fast will give us the opportunity to reach even higher throughputs. We have already tried some systems and we can go over 150 for sure, and probably to 200 in some cases. Another addition, the latest addition to the portfolio of the lossless data compression course for CAST is our ASIC4 and Snappy IP, which to the best of our knowledge is unique in the market that combines these two algorithms and gives the option to the developer to choose between one or the other algorithm. These algorithms have already been introduced in the market and have been already productized by these IP cores for CAST customers. And based on our long experience with the ZIP cores, these cores as well can reach the same kind of throughputs on both FPGAs and ASICs, 100 gigabits per second, more than 100 gigabits per second on FPGAs, and over 400 gigabits per second on ASICs. So we have a pretty extended portfolio that gives to a developer a big flexibility to choose. We have low latency cores with limited resources usage, and this includes the GZIP with static Huffman tables, the ASIC4 and the Snappy cores. In this case, the latency of the core is a few tenths of clock cycles, even for high throughput configurations. And we also offer high compression ratio cores, such as the GZIP with dynamic Huffman tables. And for more complex implementations, we can offer combinations of the above. So let's now switch to actual implementation examples and the integration process. So we discussed the advantages of using hardware over software, but in the end, what is important here is to have a hardware core that is easy to integrate. It is very important to be able to offer to a developer a core that will not need much effort to be integrated in the design, even if it is a high performance core of 400 gigabits per second. The ZIP Accel cores by CAST offer a native streaming interface, or alternatively AXI or Avalon streaming interfaces that are very, very easy to use. The same applies to the LZ4 and Snappy cores, for both compression and decompression. This interface, the standard interface there is AXI streaming, which is easily transformable to Avalon streaming for these cores. So what happens if your design and your architecture is another kind of interface? What happens if you require a memory map interface? Well, that depends on your need. Whether what you need is slave access to the memory bus, which means that a DMA already exists in your system, or a master access to the bus, whether a DMA is after all required in your system and you need it with these cores. We offer two different solutions, what we call the memory map to streaming bridge, which is a bridge that will give you a slave access to the memory bus and will transform the AXI stream interface to AHB or AXI for Lite. And as an alternative, if you require master access to the memory bus, we can offer you our AXI4 scatter-gather DMA, which will transform the AXI stream interface to from the scatter-gather DMA with memory mapped access. Both solutions are easily available. So the integration in this case is very easy. You see here a very simple example. What you only need to do is to add these cores at the input and at the output streaming interface, and you will then transform your streaming interface to memory map, which will be ready to be integrated in your system. Now let's discuss some real-life implementation examples. These two examples come from real CAST customers that will, of course, remain nameless for confidentiality reasons. The first one is for a data center application. The throughput is 400 gigabits per second on 7 nanometer TSMC technology. It required about 9 million gates and 2.7 megabits of memory on the frequency, on the system frequency of 1 gigahertz. And customer B is a networking application on an AMD Unveil FPGA device for 100 gigabits per second throughput. The frequency we reached on this device for this specific implementation was 200 megahertz, and the total LUTs were about 350,000, with about 1,072 LUT RAMs. For decompression, for the same application cases and the same customers, the logic area for the decompression core was 1.7 million gates and 1.7 megabits of memory, again 1 gigahertz of clock frequency. And for the networking application, the FPGA device, we have 212,000 LUTs and 9,000 LUT RAMs, about 10,000 LUT RAMs for a clock frequency on the FPGA device of 220 megahertz. I took the liberty to add a few more results here for ASICs for both compression and decompression, just to show you the change, that the difference that can come, that how different the size of the core can become depending on your configuration. All these cores have 200 gigabits per second throughput, and the size can change from 7 million gates to 16 million gates depending on the configuration you have, on what kind of search algorithm you implement in your history window, the size of your history window, what size of files you have. All this will impact the configuration a lot. And of course, this will also impact the latency. You can see here the orders of magnitude that will assist you make a choice. The orders of magnitude of latency for dynamic Huffman tables is around 12,000 clock cycles. This is 5-fold latency, first in, first out in clock cycles. Whether when you switch to static Huffman, even in 200 gigabits per second, the latency is only a few tenths of clock cycles, 125. And the same applies in principle for the decompression as well. Well, the memory bits are also affected by buffering of the files. The presented results are only indicative and based on the assumption of 1 gigahertz clock. If the clock is faster, because the performance is linear with the clock, if, for instance, this applies to a 2 gigahertz clock implementation, the core sizes will drop to half. All the results are scalable. So if you need 400 gigabits per second, as we discussed in the previous slides, it will be double the size. For 100 gigabits per second, it will be half the size, etc., etc. And its configuration is design specific. So whenever a developer comes to cast with a specific request, we make a specific configuration for that design. The same applies for FPGA implementations, but this again is a study for 100 gigabit per second to show you the difference between resources for dynamic Huffman and static Huffman for both compression and decompression. This again is indicative, only indicative to show you the latency in clock cycles, the orders of magnitude, and in the order of magnitude of the sizes. The results are only indicative, and we should also emphasize here is that the cores are Verilog, they are pure RTL, and they're completely technology agnostic. These cores can be and have been implemented on all major FPGA vendor cores, IPs, devices. We have customers for AMD, we have customers on Altera, we have customers in Lattice, we have results on Efinix devices and Microsemi as well. You can all find it on our website. All these cores are completely technology agnostic. For these specific results, the devices that we used was the Alveo U200 for the dynamic Huffman and Vitex Ultra Scale Plus and Versal for the static, just to give you a reference. The results again are scalable, and its configuration is design specific. Again, when a developer comes to cast with a request, we make a specific configuration for one-time design. So what should we take away from this presentation and this discussion today? First of all, lossless data compression used to be kind of a niche application and algorithm in the past years, when we had only like applications like huge data centers that required high throughput, that required these large implementations. But in the latest 5 to 3 years, we have seen that it is becoming a fundamental part of all new embedded system designs because of the new application threads and the new requirements specific for the new applications in the new markets, such as automotive, AI, aerospace, etc. Based on the information we presented to you today, you can see that there isn't a unique solution. Every case, every system, every single design is different, and we should take into consideration the requirements in order to make an educated decision. We should take into consideration the technology used, whether it is ASIC or FPGA, which device, which process, how fast is it? What is the throughput that is needed? What is the compression ratio required? What is the latency? And how much flexibility is there in between these requirements in order to make significant trade-offs? We also saw that the high compression ratio solutions will always come at the expense of more resources and higher latency. This is a rule that unfortunately we cannot break. But it's also very, very important is to have a hardware core that is easy to integrate. It is useless to have something that will give you performance when you lose 1 or 2 months to do integration of just this core. So it is important to have hardware cores for lossless data compression that are easy to integrate with easy interfaces, such as the streaming interfaces we provide and the memory mapped interfaces we can offer. So after all this information, we can see that the designer must make an educated decision, because it's relatively easy to go off track, because there are far too many parameters to take into consideration to make an educated decision on your design. This is why it is best to rely on experts such as CAST, where we bring to the table experience of more than 10 years of using high performance lossless data compression cores on ASICs and FPGA systems. So what approach do we use to assist the developer? First of all, we ask the developer to define the specifics of the requirements for this design, the throughput, the technology, the file size, and the data type. And then the very important part of this process is to define the priorities. What do you want most? What is your biggest and most important characteristic of the design? Do you need low latency? Do you have limited resources available? Or do you need to hit a specific target for the compression ratio? Based on these parameters, will give you the best solution. It's always supported by simulation results and implementation results for throughput and power performance and area. And then we can also propose accompanying cores and solutions, such as the DMAs and the bridges I presented in the integration phase before, and also encryption solutions, all based on the extended core selection and portfolio experienced by CAST. If you need more information on our lossless data compression course, please hit this link to get more information. And you can also contact me directly. This is my email. I know that my last name is a nightmare for most of you, so the easiest email address would be sales@cast-inc.com to get more information. And now we have some time for some Q&A, and I look forward to hearing and answering your questions.
Thank you very much. Great presentation, a lot of information. We do have some questions. So the first question, have you compared the described algorithms with GPEG-LS, both software and CAST FPGA implementation? It also has low latency and resource requirements, or is it worse in any parameters? Does that make sense?
So yes, the question is about the lossless image compression algorithms, the JPEG-LS ones. So the difference here is that these algorithms target different things. The ZIP Accel, the LZ4 Snappy algorithms are general purpose compression algorithms, and they can be used for any kind of data. JPEG-LS is specific for image processing. So we can use ZIP Accel for image processing. Okay, we have done it and it gives good results, but as in every case of lossless data compression, the compression ratio and performance depends on the data type. So there are cases of where lossless image compression is required, where the 870 will not work at all. You will get a very low compression ratio in the area of 1.2, 1.3. This happens specifically to some kinds of MRI applications that we have a lot of experience on. In that cases, JPEG-LS is the optimal solution, because this is what it was specifically designed for. So yeah, in that case, the JPEG-LS will be the better solution. But again, it depends on the data types.
Okay. Second question, I have a system that includes software compression. Can I incorporate hardware compression and decompression into this architecture?
So basically, yes, this is absolutely true. This is actually one of the most common applications that come to us. We have developers that have used systems with software compression and want to use hardware decompression, or want to substitute both compression and decompression with hardware cores. So this is very easy to do. This is what happens when you use software for compressing your data. You need a decompression core that would be compatible with the complete protocol of the algorithm that you will use. We offer such cores, and we have done it many times in the past. So there is a specific configuration of the decompression core that you need to use if you want your decompression hardware to be completely compatible with any kind of compression software. This also works the other way around. You can use hardware to compress your data and then decompress your data with software. In that case, any software that is compatible with the compression algorithm implemented in your IP will be able to decompress your data. There are no exceptions here. All decompression software will decompress data compressed by any configuration of a cast compression core. You can also substitute compression and decompression completely with compression decompression with hardware, or have both and alternate. It depends on your requirements. In any case, this is what these cores were born for, and this is what we do.
Great. Are the algorithms you presented optimal for image and video compression?
Well, it was partly covered by the question for the JPEG LS. These are generic compression algorithms. They are not specific to a kind of data. So the efficiency and the compression ratio these algorithms will use will largely depend on the data type. So you need to test whether they will give you a higher compression ratio than JPEG, LS, or other kinds of lossless data image compression algorithms. But in any case, a lossless image compression core has been designed for this specific case. The best strategy for its developer is to compare. When someone comes to us for lossless image compression, we will first suggest a specific image compression algorithm to start with, because in principle, this is what it was designed for. If that doesn't work, then we can use all the alternatives and study it. Okay. But in any case, what is optimized is for image and video compression is the lossless image compression algorithms. Whether a designer needs lossless image compression or near lossless image compression, or needs lossy, can accept the lossy image compression, will also guide the choice, because in that case, if lossy compression is also acceptable, this opens a complete new range of cores that we can propose. Okay. Lossless data compression and image compression algorithms are a specific part of the portfolio, whether lossy can be like normal JPEG, H.264, etc.
Okay. Since GZIP is configurable, how do I determine the configuration for my system?
So here is the thing here. As we explained during this presentation, there are a lot of parameters to take into consideration when configuring the GZIP algorithm. Configuration can be relatively easy when the developer wants low throughput, where just a single processing element will be required. But when throughputs grow and scale to multi-gigabit implementation, then because these cores are highly configurable and many things impact the performance, such as history window size, encoding parameters, file size, how you slice the data between parallel cores, etc., it is better to get assistance, educated assistance from an expert. I mean, what we do for our ZIP Accel course is, or not only the ZIP Accel course and the LZ4 and Snappy course, is we assist the developer hand in hand. We take you hand in hand in order to understand exactly what you prioritize. And sometimes the first solution is not what we choose because the customer, the developer changes their mind. They understand that they want to prioritize another thing in their design. So yeah, you need to take into consideration a lot of parameters and make an educated decision. It can be easy when a small core is required, but it can be complicated. It takes a lot of time, a lot of studies for a high throughput core.
Okay. How do I evaluate the resulting compression performance for my specific data?
So we offer the software models for both these cores that both core families, for both ZIP Accel and LZ4 and Snappy. And you will have a very clear understanding of what the compression ratio will be for your specific data types and your specific design. So you can get a first level of understanding of the compression ratio these cores will give you, even by using the simple software. This will give you an understanding of the first level. But then, in order to get an exact feel of what the exact compression ratio will be on hardware, you will need the software model, because the software model will also take into consideration the various parameters we discussed, such as the choice between the kind of encoding, the flavors between dynamic and static Huffman tables in the ZIP Accel cores, and the size of the history window for all cores. With these things also impact compression ratio, and they are not available as parameters on the open available software, and that is basically on Linux root, on anything like that. But there are software models that will assist you to have a complete understanding of the compression ratio you will get for your data and your data type and the file sizes you will use in your final system.
Okay. Final question, how do I scale my design to handle more data in the future?
So I assume the question here is if you get a core that has a specific throughput and then you want to increase the throughput in the future. So there are 3 different strategies to follow here. The easiest one, let's say, is to increase the clock speed. As we said, that the performance of these cores is linear with clock speed. So if you get the same core and a faster technology and you're able to close timing faster, you will linearly increase the throughput of the performance. But that, of course, isn't always feasible. You might need more performance on the same process, on the same design. Then, of course, you will need to sacrifice resources and parallelize the core. And the parallelization can be in 2 ways. You can either parallelize externally, so have multiple instantiations of the same core in order to increase throughput by having more than 1 streams of data being processed in parallel, or you can increase the internal parallelization of the core, which means that you will still maintain a single core and a single data stream for your data, but the core will become larger. We will have more parallel processing elements inside, and thus you will have a higher throughput.
Great. Thank you very much. Thank you, everybody, for participating in the SemiWiki webinar series, and have a good day.